All right, you guys. So as we were talking about high spin and low spin and how our d orbital electrons kind of coordinate with different ligands differently. Kind of a roundabout way of saying that. Just to emphasize, the difference here is the difference of energy that it takes, right? So we were talking about how strong ligands, also known as a low spin, are going to have to overcome more energy in order to get into these higher up orbitals. So the electrons are going to first go through and fill this bottom one. Even though, just like Hund's rule says, electrons are normally placed in orbitals in separate orbitals before filling up different ones, it's actually more favorable for them to come back down here and fill in this first row before going all the way up. However, if we're binding to weak ligands, again, just reemphasizing this, also known as high spin, they are going to remain unpaired and they're just going to go through and not have to overcome a ton of energy in order to be in their own orbital. All right. So that's kind of the order that it'll happen. Remember, it'll go through and it'll want to fill its own before coming back, whether that's high or low spin. Again, these are the tetrahedral. This is an example of how it's going to be in the tetrahedral. It's kind of the same as octahedral, but flipped. And then square planar is different. And remember, square planar is normally when there's 8 d electrons in a configuration, but not always. So I said you don't have to memorize these. Just learn them, I guess, is what I would say. They are important. You guys are going to hate me, but at this point in the video, I would love if you guys could pause it and read through this. This is from your textbook. So go ahead, take a second and read through what's going on here. All right, cool. So as I stated before, electron configurations are responsible for magnetic properties and optical properties. So let's first talk about these optical properties, right? So that has to do with light. So this right here is kind of it's not kind of, it is a ranking. This right here is a ranking of our ligand strength. So cyanide up here as a ligand has a super high field strength and a super high orbital splitting. So relating that back to what we already talked about, it's going to have a super high orbital spinning. It's going to be one of these, okay? That being said, it having a high field strength means it absorbs a lot of energy. It absorbs a ton of energy in order when light interacts with it, right? Just due to that energy difference right there. So if you remember, with light, a lower frequency is equivalent to a higher energy, right? So if this is absorbing a really high energy, it's going to be absorbing the lower frequency. So cyanide in this case will be absorbing the violet color, the low, I'm sorry, the smaller, sorry, I said frequency. I did not mean to say frequency there. The smaller wavelength, the higher frequency or higher energy. And it will be emitting. So remember, if it's absorbing whatever color it's absorbing, the one exactly opposite on the color wheel is what it will be emitting, right? So that's just a good example of cyanide. Something lower, for example, are halides down here. They have a really low field strength, a low orbital splitting. They're going to absorb colors with a higher, a lower energy, but a bigger wavelength. So for example, these might absorb the kind of the red-orange spectrum. If that's the case, they're going to emit the colors that are directly opposite of them, and they'll give off a blue-green color. So that's something important to remember about field strength, about orbital splitting. I do know that you don't have to memorize this, but have a basic idea, right? So like our halides are low, water's in the middle, and then anything with nitrogen is going to be pretty high. So that's just kind of a rough idea of what is going to be absorbing higher energy and what's going to be absorbing low energy. Again, I have added right here more information if you would like it. This kind of goes into an article about it. It has some pretty cool examples. Also, magnetic properties. Where did I put that? Oh, magnetic properties. So remember the difference between paramagnetic and diamagnetic. So why is it doing that? There we go. So magnetic properties. So let's use, so we'll say we're filling up an orbital here, right? So paramagnetic is when we, let me just draw an example real quick, when not all of them are paired, right? So this one isn't paired, this one isn't paired, this one isn't paired. So this is going to be paramagnetic. And it's going to have, it's going to be attracted to a magnetic field. However, diamagnetic, we're using kind of the same example here. Again, I'm not specifying if this is octahedral, tetrahedral. It's just to give you an idea of the different orbitals, right? This is going to be diamagnetic. Di, the way I remember this, I remember di means two, and each one of these is going to have two electrons in it, spinning opposite ways. They're going to have opposite spins, but they are going to be completely filled. And this is satisfied. It is not going to interact with a magnetic field, because it's actually going to be repelled from a magnetic field, because it is just so happy with and satisfied with the number of electrons that it has. So that's just a couple things that in terms of property that I think are important to know. So remember, that might not be everything about field strength and ligands, but it's what I find to be the important stuff. All right, so let's talk about redox reactions. So I find the best way to do these is just with examples. So let's go ahead. I've got a couple of examples. Let me pull them up and I will show you how we are able to get half reactions, how we balance redox reactions, and all that good stuff. So I have kind of the order on here. So feel free, take a look at that. And then we'll start running through them. Okay, so what I think is important to emphasize here is that your so your half reactions in acidic solution, your half reactions in basic solutions are going to be a little bit different. And it just has to do if there's H plus or OH left in the solution. Remember, your acidic conditions are going to have OH in it, and your H plus are going to have H plus in it. So I'll show you how to do that. It's the same process. We just switch one of the things, and it makes it pretty easy. So let's start with an acidic solution. So I am going to give you guys an equation, and I want you to balance it. So yeah, let's do this one. So we're gonna have HCOOH. So go ahead, pause the video and see if you can write a balanced reaction, balanced equation for this. In acidic conditions. So go ahead and try to do that. Okay, I am gonna run through this. So the first thing I want to do is I want to identify my cathode and my anode, right? So I see this, I'm isolating kind of like my metals over here. I'm going to look at the charge of these. So I'm going to see that this is a -2 charge, this is -2, +1, +1. So I don't see any charge over here. So the charge of 0. So in order to counteract this -2, 4, +1, -3, -2, this is going to have a charge of 2. Now look over here, this is a -4 altogether. So this is going to have a charge of 4. So I see that this one is going to be losing electrons. And then we're going to look at this. This is going to have, so it has a charge of -1. So this altogether is going to be -8. This is a -1. So this is going to have a charge of 7, because 7 plus -8 is -1. Okay. So now I'm going to break these up. And I'm going to set up my half reactions. HCOOH. And on this side of the equation is going to be CO2. I have MnO4 minus. On the right side of the equation is going to be Mn2 plus. So I already figured, and then this is going to be a charge of +2, obviously. So I already figured out which one is losing electrons and which one is gaining electrons, right? So this is going from 2 to 4. So it's going to be losing electrons because it's coming more positive, and that means that the electrons are going to be on the right side. We'll do that with a different color. So electrons are going to be on the right side. How many? That depends on the difference here. So 4 minus 2 is 2, so we're going to have 2 electrons coming off. For this one, we see that it's becoming more negative, right? 7 minus 2, so we're losing a charge of 5. So that means that it's going to be on the left side. It's going to be gaining electrons, meaning it's our cathode, and it's gaining 5 of those electrons. Awesome. So now, got to think it through. Come back over here and look and see that we figured out the oxidation states, we figured out the electrons. Now we're going to add H2O in order to balance. That's the O's is supposed to represent oxygens. It's not like OS as an element, it's just oxygens. So again, we're going to grab a different color. See that there's 4 oxygens over here, and I have none on my right side, so I'm going to add 4 H2Os, and then I have 2 and 2. I actually don't have to add any water to those because that is even. Next, we are going to add H pluses in order to balance this. So I see now that I have 8 H pluses, right? 4 times 2. That's balanced. And now I have 2 over here. I don't have any over here, so I'm going to add 2 H pluses onto this side. So this looks good. This shows that I have my balanced half reactions, which is super nice and super convenient. Now what we're going to do is in order to find the overall reaction, so we've created all of our half reactions. We don't have to do this last part because that's only if it is in a basic solution, and we'll do that next. But it's in an acid, we have H+, so we're good there. Now we have to find the overall reaction. We find the least common denominator of the electrons. So I have 5 electrons in this one and 2 in this one. So the least common denominator of this is going to be 10. So I'm going to have to multiply this entire thing by 2, and this one by 5. That way, I have an equal amount of electrons and they'll cancel out. That's the overall goal of finding a balanced equation, is canceling out those electrons. So I'm going to distribute this 2. So this is going to be 2, 10, 16, 2, and 8. I have that all distributed. So this is going to be 5, 5, 10, and 10. So I have that all distributed. Now, what we're going to do is we're going to simply add this up. So the secret with adding this up is you look on opposite sides of the arrows, and anything that are on opposite sides of the arrows that are the same can be canceled out. So for example, I have 10 electrons on my left, 10 electrons on my right. So those can cancel out. I have 16 over here, 10 over here, so I can take out those 10 and turn this into 6 H pluses. Now I'm looking and I don't see anything else. So now I just bring down everything on the left side with their coefficients, remember, plus 6H plus, and everything on the right. And this will give us our balanced reaction. And this is in acidic conditions. So this is our answer here. Cool. So now let's figure out how to do this in basic solutions. Remember, this was our acidic solutions. All right. So for our next example, let's do chromium 3 plus Br2. That's going to be going to CrO4 2 minus plus Br minus in basic conditions. All right, guys, so let's get into it. So the first thing I'm going to do is I'm going to come over here and I'm going to figure out my oxidation states. So these are each adding a negative charge, and there's 3 of them, so I'm going to have -3. So that means I don't see a charge over here. So this is going to have a charge of 3. Look over here. So this is going to be a -8, but I'm allowed to have -2. So this is going to have a charge of 6. It's going to have a charge of 0. And over here is going to have a charge of -1. All right. So let's break these up. Bring my chromium and put it in its own half reaction. One with the chromium. So CrOH3. Let's go into CrO4 2 minus. You can break them up into the basics, like I'm doing right now, of their half reactions before you figure out the oxidation states. This is just kind of what I like to do. That way I'm just ready to add in my electrons as we go. So I see that this is becoming more positive, that the chromium is becoming more positive, right? It's going from 3 to 6, so it's going to be losing electrons. It's going to be losing those negative charges. How many of them? 3, right? 3 minus 6 is 6 minus 3 is 3. And we look at this, and this one's kind of tricky. What we have to do first is we have to balance this. We have to balance this half equation. We only have one bromium over here. And we have to change that to a 2 in order to get a balanced reaction. It's important to note that, yes, each bromium is gaining only one electron, but because there's 2 of them, we have to include both electrons into our balanced half reactions here. So each bromium is gaining only 1 electron, but there's 2 of them, so we have to add those 2 electrons. So next, we have to balance the oxygens. So I look over here, I have 3. Oh, I set that up. There we go. So I have 3 oxygens on the left side of my chromium, and I have 4 oxygens on the right side. So I'm going to add 1 H2O over here. For the bromium, we don't have to do anything. Now we look and we have to balance the hydrogens. So over here, I'm going to have 3, 4, 5, and then none over here. So I have to add 5 H pluses. All right. So my question for you guys, are we done? Are we done with our half reactions? Did we finish all of our half reactions? We haven't. This is a basic solution. So how do we change this? How do we change this into a basic solution? So what we're going to do is we are going to add 5 hydroxides to each side, essentially changing this into a basic solution. So we're going to add it to the left and to the right. What we're actually going to do now is we're going to sum the H plus and the OH minuses together to create 5 H2Os. And remember our rule that if we have something on the left side of an arrow and something on the right side of an arrow, we are able to cancel them out, right? So we are going to take this out, subtract one of these guys, and we're going to end up with 4 H2Os. So that is super nice. We are going to be able to just take those out of the equation now. Now, this is a balanced, these are balanced half reactions in a basic solution. The next thing we're going to have to do, if we want to get the balanced reaction, to find the overall reaction, we need to find the smallest common denominator of these 2 things, of the 2 electrons, right? So I have, right here, I have 3 electrons. Over here, I have 2. The least common denominator is going to be 6. I'm going to put these in parentheses. I'm going to have to multiply this entire bottom one by 3, top one by 2. You get 2, 10, 2, 6, 8. And then over here, I'm going to get 3, 6, and 6. So now in order to finish this up, we're going to sum them together. Remember, we're going to cancel things on the opposite sides of the arrows. And that's everything that we can cancel. And then we bring down everything on the left side. Two. Make sure that's the right answer. And yeah, we are good. So that's how you find a total, or like an overall balanced equation in basic solutions. So we covered a lot in this. I think this kind of summarizes everything that you really have to do with redox reactions. You find the oxidation number of the elements. You identify what's being oxidized, what's being reduced. Remember, whichever one is losing electrons is going to be oxidized, and whichever one is gaining electrons is the one being reduced. You are figuring out how to balance the redox reactions. You are finding the half reactions, finding the overall reactions. So I think this is really good practice for your guys' test. Again, if you have questions, there are more practice problems that you can do over here. Next, we're going to talk a little bit about voltaic cells. So before we talk about that, I think we need to talk about reduction potentials. So remember, when you're gaining electrons, you are being reduced. So your reduction potential is essentially talking about how likely you are to receive an electron, how much an element wants an electron. Greater reduction potential, more likely to be reduced. So if we're looking at this example over here, we see we have copper. So let me try to get both of these in the frame here. So we have copper, the Cu2, going to the solid, plus 2 electrons going to the solid copper. And we have zinc. And zinc's going to be down here. So we see that copper has a much greater reduction potential than zinc, right? And for that, it's going to be taking the electrons from zinc in a voltaic cell. Remember, this is under standard conditions because the concentration is 1 watt, and it's going to be taking those electrons and causing this energy to flow through the voltaic cell. Remember, this is under standard conditions, and the way that we can calculate how much voltage or like how much energy is really coming through is by this equation right here. So let me erase some of this. It's getting kind of messy. So we know the E cell is going to be equal to the reduction potential of the cathode. So the cathode is 0.342 minus the reduction potential of the anode, and that's going to be a negative 0.762. And if we do the quick calculation for this, we're able to see that it comes out to about 1.104 volts, which is pretty cool. So yeah, I think that's all we really need to cover about voltaic cells under standard condition. Remember, that's what I need to emphasize here. This is under standard conditions. With the 1 molar concentration of each one of them, you're able to do this. A little bit about like naming. So the oxidizing agent or the oxidant and the reducing agent or the reductant is it's going to seem a little backwards. So the cathode is going to be the oxidizing agent. It's what's doing the oxidizing. It's the one taking those electrons. And the reducing agent is the one that's giving up the electrons. So in this case that we just talked about, the copper is going to be the oxidizing agent and the zinc will be the reducing agent. So just to kind of have those words in your mind as you go throughout this. I also want to say it's really important that you know how delta G and K relate to E of a cell. Know that as a reaction proceeds, the energy will decrease, and at equilibrium, it'll equal 0. Just want to kind of draw your attention to, that was really bad, to this section right here. Just kind of understand how they all relate, and then know how to use these equations. There's tons of equations, tons of practice problems in your SmartWorks and in your book in order to get practice using these equations. I had a question from a student. They wanted me to cover, how do we determine N? How do we determine the number of electrons that are going to factor into these equations? And that comes from this. This is the long way in order to get to it, but if it's required, you find the least common denominator of the electrons. In this case, it would be 6, and that would be your N. It's the electrons that are being shared, or that are trading off for your anode and your cathode. So that's how you find N. And then the rest of these are constants, right? So you know your R constant, T, is know that that's in Kelvin. Then your N is going to be your number of electrons that are being shared between the cathode and the anode. Under non-standard condition, it's going to look like this. So I would encourage you to take the time to I think this is a really cool explanation of all of it. It's just kind of like a video that it's an image that I just took off of the internet. It kind of shows the equation, the Nernst equation, and then how you can kind of change that to get more usable numbers, essentially. But under non-standard conditions, so when a cell is not, when a cell does not have 1 molar concentration, for example, you're going to use this equation. So you're going to plug in your E cell, and you find that by this equation up here, right? So you find your E cell, and then you plug in your values for here. You figure out how many electrons are getting traded out, and then you do your ln of Q. Remember, Q is going to be the concentration of your products over the concentration of your reactants. We've been doing that for so long. It's not a new concept. You're not going to include solids and liquids. You're going to include gases and aqueous. This can also, something that's tricky is this can also be partial pressures. So just be aware of that. Due to the gas laws, we're able to use partial pressures for our products and our reactants. So remember, this is non-standard conditions. You can also use this for concentration cells, right? So this is kind of a neat example here. We have copper on both sides. It's the exact same thing. We have our salt bridge, but what's differing here is the concentration of Cu2+, the aqueous concentration of that. And you're able to use this same Nernst equation, right? So you have your E cell, and that's going to be your E cell naught minus RT over NF of ln Q. So your E cell here is going to be 0, right? Because it's just your cathode and your anode are the same thing. They're both copper, so it's going to be X minus X, or whatever that number was. I think it was like 3. We'll just actually put it in as 3.42 minus 3.342. Then you have your values here that you know, and then you put your ln of Q. Now, for your ln of Q, some people get tripped up, but you're going to put the less concentrated one on top and the more concentrated one on bottom. And then that's going to give you, so remember, these are going to add up to 0. And you'll just kind of be left with the negative RT over NF of your ln Q. Remember, less concentrated on top, more concentrated on bottom. And you're able to figure out the voltage of that cells. So membrane potential, what's interesting about these is they are going against the gradient. They're really similar to concentration cells, except they're putting in energy. Energy, a lot of times in biology, and I'm sure a lot of you know this, is shown with the ADP to ADP. So this, when you set this up, your E cell is actually going to be a negative number. And then you are going to set that equal to 0 for your E cell naught, right? So we're just putting this in, and then you're able to solve for the other values over here, whether that be your quotient gradient or not. Last thing before this turns off on me, read these. You guys aren't going to like me for that, but the book explains it way better than I do. This is going to go over corrosion, electric cells, batteries,